All right, so the last thing we left off with in 5.1 part 1 was converting from polar to rectangular. Now, we're going to start by reversing that. And I think that's the last thing that's actually in this section. In rectangular, can someone remind me, what are the two things that they give you to describe a rectangular coordinate?
X and Y.
They give you the x and they give you the y. So that's like they would give you, if you're trying to get to this dot, they would give you this, which is the horizontal movement, and they would give you this, which is the vertical movement. What are the two things that you need to write a point in polar? It's not an x and a y. Yeah?
Radius and theta.
You need a radius and you need a theta. Your radius, if you imagine turning this into a circle, is the distance from the origin to that dot. That's your radius. And your angle is the amount of rotation between the red line up to the black line. That's your angle. So now we're going to convert an x and a y into an r and a theta. Let's start with getting r. If you know x and you know y, you know 2 out of 3 sides in that triangle. How can you get the third side knowing the other 2? Yeah. Think of like it's from geometry.
A squared plus B squared plus C squared.
Yep. What is that?
Totally forgot.
Pythagorean.
Yeah, we use the Pythagorean theorem. So can you tell me what the theorem would be using these letters instead of the ones that you just gave me?
X squared plus Y squared equals R squared.
Yeah, I'm going to write this down nicely on the next page. But that's the formula to find r. It's x squared plus y squared equals r squared. Okay, so actually I think I have it. I'll write it down on the next page. So that's how you're going to get r. Use the Pythagorean theorem. And now we need to get theta. What position is side x relative to theta? That is adjacent. And what position is side y? Yep, opposite. What trig function involves opposite and adjacent? Yep, tangent. So tangent of your angle would equal, what are we calling our opposite and what are we calling our adjacent? Y over x. Now, when you write the coordinate, it's not tan theta that goes there. It's theta. So you need to get rid of tan. We've done this before. How are you going to get rid of the tangent function? Yep.
Take each inverse tan.
Yeah, you're going to take the inverse tangent on each side. That's going to cancel the regular tangent. And now you have a formula for the angle. It's the inverse tangent of y over x. So that's pretty much, I have to add one thing to it. But that's how you find your angle. And above is how you find your radius. So let me write that all down nicely. Now, it does matter the quadrant you're in. So the first thing that you want to do when you are converting from rectangular to polar is figure out your quadrant. Do you have to necessarily graph it? No. Like if I give you the point -4, -5, and you know that's quadrant 3, that's good enough. Right? You just need to know the quadrant that you're in. If you are in quadrants 1 or 4, you can use exactly the formula I just showed you on the other page. Theta equals inverse tangent of y over x. If you are in quadrants 2 or 3, that doesn't quite work. You have to make a small adjustment to it. If you're in quadrants 2 or 3, you can still do the inverse tangent of y over x, but you have to add 180 to it. Okay, you have to add 180 if you're working in degrees, or add pi if you're working in radians. Now, between these two formulas, it covers quadrants 1, 2, 3, and 4. But that doesn't cover everything. Where else could you be when you're trying to find an angle besides in quadrants 1, 2, 3, or 4? Yeah? You could be where?
On the left.
Well, you're always going to be on a circle like this, and the circle is around the origin, so you'll never be at the origin. Where else could you be? Yeah? You could be on an axis. If you were at that point right there, I don't know the y value of it. It's up. Maybe it's up 2, up 3, who knows. But I do know the x value. What's the x value of that green dot? 0. What would happen if you try to use either one of those formulas and plug in a 0 for the x value? Why not?
You can't divide by 0.
You can't divide by 0. Right? So if you have a coordinate that ends up on this axis, your x value is 0. You can't fill in a 0 for x. That's why these formulas will not work. So what do you do if you're on an axis? Well, you have to memorize the answer. It's either 0, 90, 180, or 270. It's one of those 4. So now, between memorizing the answer if you're on an axis and using one of these formulas if you're in a quadrant, it covers everywhere the angle could be. Okay, so that's how you find your angle, using the x and the y. And what's the other thing you need in polar? Besides the angle, you need the radius. And what was the formula we had? This formula works in every quadrant. There's no change.
X squared plus y squared
X squared plus y squared
equals R squared.
equals r squared. It's just the Pythagorean theorem. Okay, and this is how you change from rectangular to polar. So in the last section we did the other way. Now we're doing rectangular to polar. Okay, so let's try this one. 2, -2. Whether you want to find r first or theta first, it's up to you. You got to find both. You can do them in either order. But regardless of the order, figure out your quadrant first. What quadrant is 2, -2 in? We don't need a perfect stretch. Let's just need a quadrant. Yeah? 4. Somewhere right about there. Right 2, down 2. So let's do theta. What's the formula to find the angle when you are in quadrant 4? Yeah?
Inverse tangent, so y over x.
Inverse tangent of y over x. When I type that in, that's really just the inverse tangent of what number? -1. Okay, so on your calculator, do inverse tangent, -1, and you get -45 degrees. That is your angle. Okay. Radius. R squared equals x squared plus y squared. R squared equals x squared plus y squared. Make sure you put parentheses around that -2 if you do it on a calculator, because it won't work if you don't. But it's better to, I think we can handle that one in our head. What's 2 squared? What's negative 2 squared? So that means r squared is 8. So r is how much? Yeah. So what do we have to do to get rid of squaring? We have to take the square root. So r is the square root of 8. Or if you simplify it, yep. Okay, so one way you could see this answer, like say it was multiple choice, I could write 2 root 2, comma, negative 45 degrees. That is correct. What would it be if I said to you to write the answer, but not with a negative angle? I want a positive angle instead. This gets into what we did a little bit ago. What would your angle be? Think about what you can do to an angle to make it positive. Yeah?
315.
It's 315. So that's negative 45. That's 315. Okay, so which answer is correct? Both. If it was multiple choice, you wouldn't see both of these listed. You'd see one or the other. Right? And there's 2 other ways you could write this. You could write it with a negative radius and get 2 more ways. As long as you can get one way, you can figure out all the other ways. Okay. Any question on that one? All right, let's try this one. Negative 4, negative 5. What quadrant is negative 4, negative 5 in? Yeah? 3. Negative, negative, which is right around there. I'm not sketching it to sketch it. We're just putting the dot there so we remember quadrant 3. If we're working in degrees, what's my formula for theta in the 3rd quadrant? Remember, degrees and radians, you've got to make an adjustment, but it's different. Yep.
180.
180
Plus inverse tangent of y over x.
plus inverse tangent of y over x. Now, if you flip the y and the x, will you get the same thing? No. When you divide 2 numbers, the order is important. It has to be y over x. If you do x over y, it will be wrong if these numbers are different. Okay? If they were the same number, like a 2 and a 2, well, then if you flip them, it doesn't matter. But always do y over x. So I got negative 5 over negative 4. If you want to cancel the negatives, you can do that. And now you type it in. 180 plus inverse tangent of 5 over 4. That's 231.34 degrees. Okay, so that's the amount of rotation, which makes sense because it should be between 180 and 270. And it is, 231. And what's going to be my formula to find my radius? I'm going to have r squared equals, yep.
Negative 4 squared plus negative 5 squared.
So r squared equals 16 plus 25. 16 plus 25 gives me how much?
41.
41. And what's my last step to get r by itself? Square root. Now, since the angle was already rounded off to a decimal, I would say why don't we just round the radius as well. Okay. So square root of 41, it's about 6.40. Okay. So writing this point in polar, you would do 231.34, comma, whoops, other way around. 6.4 comma 231.34. I'm sure it's picking it all up.
Oh, I'm sorry.
Yeah, it's gonna mess things up.
Who's just trying to sleep, so I'm waking him up.
Okay. So 6.40, comma 231.34. Radius, comma theta. If you switch the order of the radius and the angle, that doesn't work. Yeah, that's wrong. It's like switching x and y. It's a different point. All right. So any question on that? Yeah.
So, if we were to round off the angle, or theta in this case, do we have to convert the square root into radians?
Well, I'd say generally when they do an answer, they're either going to use decimals or they're not going to use decimals. If you wrote an answer like this, and I didn't say whether or not to use decimals, I mean, I would mark that as correct. 231.34. That's fine. But I think our book either uses exact or uses decimals. They don't mix the two.
Okay.
Yeah. Okay. Yeah, it's a good question. Any other questions on that one? Okay. So the last thing we're going to look at, we're not going to finish this, is complex numbers. So when we're dealing with complex numbers, the first thing I like to do is just look at all the numbers that we know about, different number sets, and see where do complex numbers fit in to the big picture. First of all, as far as applications of complex numbers, well, the applications are pretty complex, right? They're pretty advanced. So complex numbers are not the kind of numbers that most people would use in everyday life. So that, for us, we are not really going to do applications. We're just going to learn how you do arithmetic. Add, subtract, multiply, and divide. Okay, the applications, that would be a kind of a higher level thing that we don't do. So what I want to do first, though, is just start out with the simplest kind of numbers you can have that you would like learn about, in like kindergarten. What kind of numbers what's something really, really basic you can do with numbers? It's still math, but it's extremely basic.
Add.
More basic than arithmetic.
Count.
Count, right? When you count, you start with what number?
0.
So if I was going to count, I'd say there's 0, 1, 2 people in that row.
Oh, it depends on what you're counting.
Depends on who I'm counting.
On what you're counting.
Oh, what I'm counting. Well, if you're counting actual objects and the objects are in front of you, what number would you start with?
I guess you could start with 1.
That would be a good idea. Yeah, you start with 1. If there's no objects in front of you, you wouldn't be counting them anyway because they don't exist. But if you're counting, 1, 2, 3. So those are the simplest kind of numbers you can have. Those are called counting numbers. Now, when we start to introduce arithmetic, that's when everything went downhill, right? Adding, subtracting, that's when math started getting hard. Arithmetic, we can run into problems. With addition, you wouldn't, right? Could someone give me a counting number? Any counting number you want. Yeah? 5. Okay, so counting numbers start at 1 and they go up, but they don't have any decimals or fractions. And then give me another counting number. Yeah?
15 billion.
15. If I take those two counting numbers and add them, no problem. Right? But if I try to take those two counting numbers and subtract them, we're going to run into an issue, which I'll show you in a second. Yeah, when you add a counting number to another counting number, you're fine. The answer you get is 20, and that's also a counting number. But try subtraction. 5 minus 15. Right? When you do 5 and you take away 15, do you get an answer that's a number you would use when you are counting things? No. So the problem is, if you only understand counting numbers, which maybe like somebody in kindergarten or first or second grade would, if you put 5 minus 15 down, they might look at that and they wouldn't know what to do. They'd say, you can't take away more than you have. That's not possible. Well, it is possible. You just have to expand the kind of numbers that you know about. So the next kind of numbers we expand to are what are called whole numbers. Now, whole numbers don't even deal with this situation. all whole numbers deal with is Chad's favorite number, 0. Okay, they give you a way to represent the idea of nothing. All right, when you're counting, you don't need the idea of nothing, right? Because if there's nothing in front of you, you're not counting. So if I say count how many microscopes are in this room, well, there's no microscopes, so you're not counting them. So you don't even need a number that represents it.
What?
But when you have 0, that's called the whole number system. So whole numbers just include 0. They don't include anything else other than 0. So they start at 0, and then they go 1, 2, 3, no fractions, no decimals. The next kind of numbers deal with this situation. They allow you to have numbers that represent even less than 0. Up until now, we don't have that. And when you're in like first or second grade, I don't think they learn about these kind of numbers yet. I don't know. But those are called integers. So each time we expand the set of numbers, we're allowing ourselves to do more and more kinds of calculations. That's why we're expanding them. Now, with integers, we've solved all the problems with adding, subtracting, and multiplying. If you give me any integer, like 3, and another integer, -5, if I multiply them together, what do I get? And that's fine. That is an integer. Integers include positives and negatives. They don't include fractions and decimals. But numbers like -3, -2, -1, 0, 1, 2, 3, 4, 5. Those are all integers. So if I take an integer times an integer, I'm good. I get an integer. How about an integer plus an integer? What's 3 plus -5? -2. That's an integer. No problem. And what if I did 3 minus -5? That's an integer minus an integer. No problem. 8 is definitely an integer. But what if instead of doing that, I did 3 divided by 5? Is that an integer? No. And if you physically try to do that, that's like me saying, I want to take these 3 objects and I want to give them out to 5 people. I can't do that. The only way I can give 3 things to 5 people is if I start breaking them into pieces, fractions of the original thing, parts. And those are called rational numbers. For most everyday kind of math, rational numbers are probably as complicated as people would use. Right? When you're buying something at a store, the item might not be $10, might not be $11, it might be $10.38. So that's $10.38 of the next dollar. That's a fraction. When you're cooking, you might not need 2 cups of flour or 3 cups of flour, you might need 2.5. It's 2 cups and then a fraction of the next cup. So rational numbers are used in everyday life quite a bit. So rational numbers are all the numbers in math you can write as fractions. Does anybody know what you call the numbers that you cannot write as fractions? It's the opposite of rational.
Decimals.
Well, this is a decimal, but it's rational. So there are certain decimals that are rational and certain ones that are not. And there's a name for the ones that are not. That's an example of one of them. That's a decimal, pi. But you cannot write it as a fraction. Yep. It's irrational. So irrational are the numbers in math you cannot write as fractions. What would be an example of an irrational number? Square root of 8. Okay. It's a little bit more advanced kind of number. It's a number that has a decimal. Right? If you plug that in on a calculator, you can figure out it's 2 point something. But it can never be written as a fraction. It's impossible. You cannot write the square root of 8 as a fraction. Another number you can't write as a fraction is pi. And it's not like you could say, well, maybe someday when computers get better, we'll be able to do it. No, you'll never be able to do it. You can prove that you can't do it. Once you prove you can't do it, that means you can never do it. It's not possible to write these as fractions. If you take all the numbers that you can write as fractions and the numbers that you can't, that's called the real number system. And in Algebra 1, those are the kind of numbers you study. But just like when we tried to do subtraction, and we had a question mark because we didn't know about negative numbers, we invented negatives. So now we can do that problem. Just like when we tried to do 3 divided by 5, we didn't have the idea of pieces of a number. But you can have pieces and parts of a number. That's why we invent rationals. Well, if I write down something like this, that is impossible to do. Right? So if I showed that to somebody in Algebra 1, they might say you can't do that. Because you're trying to find two numbers that are the same and multiply to give you -4. Well, if you try 2 times 2, that's not -4. And if you try -2 times -2, what does that give you? That gives you 4. So how can you multiply two numbers that are the same and get a negative? Well, you can't with real numbers. So if all you understand is real numbers, even if you try it on a calculator, square root of -4, let me put the calculator, I'm going to put the calculator in like Algebra 1 mode. So this is like what somebody in Algebra 1 would think. It doesn't say that it gives you an error, but it doesn't say that it can't do it. It just says that the answer is not real. Do you really want to know what it is? Okay, that's basically what it's saying. So in Algebra 2, you learn about numbers that are not real. So now, when you try to type in something like square root of -4, it doesn't give you an error anymore. It just invented something to represent the answer to that problem. Just like we invented negatives, just like we invented fractions. Okay, we invent I. And that stands for imaginary. So imaginary numbers, they're their own group of numbers. Much more advanced than other kinds of numbers that we work with. Applications are more advanced. And if you take all the numbers that are real and you take all the numbers that are imaginary and you put them all together, you get complex numbers. So complex numbers are like the big group of everything. So I wanted to try to show you where complex numbers fit in. Complex numbers include everything. Every number that you've studied pretty much, at least in this class, has been a complex number. Up until now, I think we've mostly focused on real numbers. We might have did a little bit with imaginary. Can't remember. But that's kind of our number system diagram. Okay, so when we come back next time, I'll start by explaining what a complex number is. Okay, so next time we have class, we'll probably do all of A4, and then we're in good shape. We only have one section left after that. We're done for the week. All right. So as far as homework tonight, there's no homework on the number system diagram. That'll be tomorrow night. The only homework is what I had on the board, and I'll put that right back up. You know what? Since the homework is at the end of yesterday's video, I'll just refer you to that for the homework. Okay, so the homework is in yesterday's video.